We've gone over all the ways to talk about concentration of a solution. Molarity, parts per million, percent by mass, percent by volume. Now we're going to talk about one of my most favorite topics in chemistry, and that's going to be boiling point and what it is. Before we can talk about boiling point, we have to talk about temperature, atmospheric pressure, and vapor pressure. So that's what we're going to be talking about today. So, temperature, a measure of the average kinetic energy of an object. And remember, kinetic energy is energy of motion. Every object has either motion, like gas molecules have the most motion, solids, some solids can just vibrate, but everything has either motion or vibrational ability, except at one particular temperature, and that is going to be number 3, and that's going to be called absolute zero. And absolute zero can be expressed in two ways. It's negative 273 degrees centigrade, negative 273 degrees C, or for the gas laws, we can't use centigrade, we must use Kelvin. And remember, it's not degrees Kelvin, it's just plain Kelvin. And so to find out centigrade to Kelvin, you just add 273 degrees to it. So add 273 degrees C and you get Kelvin. So for absolute zero, the zero is Kelvin. So it would be this, 0 Kelvin. Remember, that's the temperature at which there's no vibrational motion whatsoever. It's kind of theoretical. I don't think we can get down to that temperature. Okay? Everything else has some type of kinetic energy in it, except at absolute zero. Okay, now the next thing we have to talk about is atmospheric pressure. So, atmospheric pressure, the pressure pushing down on us. So it's a column of air directly above us, and it extends to almost outer space. And it's not like you walk outside and go, oh my gosh, this atmospheric pressure. No, you can't feel it, but it is there. It's a column of air pushing down. Okay? Now, the big deal is it's the same atmospheric pressure at a certain place on Earth, and it's called standard pressure. And standard pressure takes place at sea level. Now, standard pressure, it can be in 4 different ways. Number 1, standard pressure can be said to be 1 atmosphere. That's usually at sea level. 1 atmosphere is also equal to 1013 kilopascals. My most favorite is 760 millimeters of mercury. But that's so long to say 760 millimeters of mercury. I like 760 torr. Now, how'd they come up with 760 torr? Well, this guy about 1620, his name was Torricelli, and he figured out how to do a barometer using mercury. So he found out that the air pressure pushing down caused mercury to stay in this elongated tube, and when he measured it, it was somewhere right around 760 millimeters of mercury. And then when he went up into the, I guess, the Italian Alps, there was less pressure pushing down, so more mercury fell out, so his barometer went down. So the higher you go in elevation, the lower the atmospheric pressure gets. And that's going to be a big, big thing coming up when we talk about boiling point. So that was Torricelli in about 1620. He discovered the barometer and air pressure. Okay, so that's air pressure. Now, the converse is true. We went to a place near the Dead Sea in Israel that was about 1,000 feet below sea level, and if you're below sea level, the atmospheric pressure would be greater because the column of air over your head is longer. My sisters live in Boulder, Colorado, 13 miles above Boulder, And they're at 8,000 feet. So that means the atmospheric pressure where they live is much lower than it is in Elmira or sea level. Okay, so the next thing we got to talk about is vapor pressure. Vapor pressure, the pressure exerted upward from a liquid. Well, here is a beaker and there's water in it. And it's not, vapor pressure is just not exerted upward, it's also exerted on all sides. But what we're concerned with is the vapor pressure exerted upward. Okay? Now, this vapor pressure is ruled by something, and this is an important part. Number 2, vapor pressure So vapor pressure is ruled by temperature, not volume. If this water in this beaker were the same temperature as Seneca Lake, well, then there's way different volumes, but the vapor pressure would be the same. So if two liquids have the same temperature, they have the same vapor pressure. And in order to increase the vapor pressure, you heat it up, just like it says. Vapor pressure is ruled by temperature. So if we think of vapor pressure pushing up from a liquid, and then remember, atmospheric pressure is pushing down. These are going to be the two key factors when we talk about boiling point. So now we have to talk about liquids that have high vapor pressures and liquids that have low vapor pressures. Now, it says water has a low vapor pressure. Well, what does that mean? That means that water really doesn't turn to vapor quickly. Well, why is that? Well, you have to remember, water is a strong dipole. Which is held together with strong intermolecular forces. And these strong intermolecular forces are called hydrogen bonds. So that means water doesn't evaporate quickly because all the water molecules are held together by hydrogen bonds. So in order to make water evaporate, you have to break the hydrogen bonds. So, any liquid that is held together by a strong dipole is going to have hydrogen bonds. And usually the only three in high school chemistry that you have to know, H2O, ammonia, NH3, and HF. Those three are strong dipoles and they will be held together by hydrogen bonds, and they would have a very low vapor pressure, which means they evaporate slowly. Okay, now let's go to the reverse. Okay, so liquids with high vapor pressures, that means that they evaporate quickly, all right? They have weak intermolecular forces. In other words, the bonds between the molecules are so weak that once you open up the cap, the bonds break. So this evaporates very quickly, and the bonds that are weak between these molecules are called van der Waals forces. Now, what kind of molecules have van der Waals forces between them? Usually non-polar molecules. The best example of non-polar molecules held together by van der Waals forces is this. Gasoline, most petroleum products, gasoline, ether, butane, propane, octane, all those things are non-polar molecules and they don't really attract each other. So they are attracted due to van der Waals forces because you get them so close together and you slow down the molecules that they attract for just a short time. And then if you release the pressure or heat them up a little bit, boom, they're gone. So liquids with high vapor pressures usually means they evaporate quickly. fingernail polish remover. But the main one is gasoline or petroleum products. Okay, so now you know vapor pressure, the pressure pushing up from a liquid. Okay, so the boiling point. This is really easy to remember. When the atmospheric pressure pushing down equals the vapor pressure pushing up. What happens is when those two equal each other, then the water will boil and it will turn from liquid to gas anywhere in the liquid. It's not like evaporation. Evaporation only occurs at the surface at all temperatures. Okay? So boiling occurs anywhere in the liquid column as long as the two equal each other. So there is the atmospheric pressure down equals vapor pressure up. Now remember, this boiling point is also controlled by elevation. So the standard boiling point at sea level is 100 degrees C. So I'm going to write that down. So here it is. The standard boiling point at sea level is normally 100 degrees C, and if we change that to Kelvin, you add 273, so it's 100 degrees C boiling point is also 373 Kelvin. Okay? So that is what the boiling point should be. Now, in Elmira, where we are, we're about 868 feet above sea level. So the further up you go, the less atmospheric pressure pushing down, so you don't need as much vapor pressure pushing up to equal it. So in Elmira, the water boils at about 99 degrees centigrade. Now, like I said before, my sisters live in Colorado. They live at 8,000 feet. That's over a mile and a half up. So the column of air above them is not very tall. So they have much less atmospheric pressure pushing down, which means they don't have to put a lot of vapor pressure pushing up. Remember, vapor pressure is ruled by temperature. So the boiling point at 8,000 feet is much less than 100 degrees C. That's why if you bake or cook, if you look at the directions, it says cook at a higher temperature or leave in oven longer at higher elevations. Because the boiling point, so where my sisters live at 8,000 feet, at 8,000 feet, the boiling point is 92 degrees centigrade. And that's 8 degrees lower than it is at sea level. So you have to cook things longer or at a hotter temperature. Or you can use a pressure cooker. So let's talk about a pressure cooker. They're great, especially the new ones. So a pressure cooker makes the atmospheric pressure inside the pressure cooker much higher. So if the pressure inside the pressure cooker is super high, that means the vapor pressure has to be much higher to equal it, to make things boil inside. And what that does is, since you have a higher pressure pushing down, you need much more vapor pressure pushing up. And how do you get much more vapor pressure pushing up? You keep on heating it up. So the boiling point in a pressure cooker is much higher than just an open pot that's boiling on the stove. So pressure cookers, since they can get higher boiling points, cook food faster. Okay? So remember, boiling, atmospheric pressure pushing down. If it equals the vapor pressure pushing up, the water boils anywhere in the liquid. Remember, that's way different from evaporation, because evaporation only takes place at the surface of, let's say, a mud puddle. Okay? All right.